In biology, we do need food. Food is going to act as our fuel in the same way in which you go to the gas station, you put gas in the car, the gas will be combusted in order to make the car move. Or you plug in your car and you give enough electrical energy in order for that car to then move from the electricity which it has received in terms of a charged battery. What is unique about biology right now is how these particular items, such as cake, pasta, buns, potatoes, meat, fruit, bread, milk, all of these are made up of chemicals. And we looked from last unit that these particular chemicals, CHNOPS, are the most common found in organic beings such as ourselves. What's fascinating is each of these materials on the table here are predominantly made up of these, if you measure them in terms of proportion, but yet when they combine, they can form different types of properties. That's this concept called emergent properties. If we look at the ways in which the chemical bonds form, whether it's going to be, for example, a single bond between carbon atoms, or perhaps a single bond between a nitrogen and a carbon, or even perhaps a double bond between a carbon and an oxygen atom, all of these are going to lead towards different types of properties. A classic example would be sodium, which is a solid metal. When placed into water, is highly reactive. Same thing as chlorine, which is a gas. It can evaporate quite readily when it's in air, and it is very, very, very poisonous. However, you combine the two and you get something that all of you are familiar with, that is table salt. Thus, the property that chlorine gas alone and the sodium metal alone had, when combined, they formed something called table salt. That's a very general idea of what we mean in terms of an emerging property, that elements by themselves have one type of reaction or one type of property, but when they combine, they have something very different. Same thing here. When we look at our meal, for example, a hamburger. Hamburger is made up of protein, carbohydrates, complex in that case, simple carbohydrates. All of these can be used as fuel. So, for example, for those who were at Congé last year, we saw Mr. Bell in the dunking booth. In order to do any type of movement, he needed fuel. This fuel is used by our bodies to predominantly make ATP. Also, it can be used to store energy or to make more muscle. Just for example, if we look at this hamburger patty, it is made up of predominantly protein, a little bit of fats. Yet when our digestive system is able to take this protein and using enzymes, it can take this protein, which is considered to be a polymer, and it can break down this protein into small monomer units called amino acids. So in this chapter, we're going to see how monomers and polymers are able to combine and recombine in terms of forming different types of organic molecules. One of the things is that all organic molecules are always going to contain carbon and hydrogen. Some, such as protein, will also contain nitrogen and sulfur. Some, such as DNA, will also contain phosphorus. Many of them also contain oxygen. So this is where we get our little CHNOPS. Okay. The other thing is that when we look at them, all of these particular lines here, as we learned from last time, equal a single bond. It's a chemical bond. In this case, it is going to be a single covalent bond. Thus, 2 electrons are shared between the elements themselves. Every now and then you might have heard of, for example, a unsaturated fat. It simply means that the carbon atoms are not surrounded by hydrogen anymore, but rather there might be a double bond in between 2 carbon atoms. So the idea is that the chemical bonds, often when we're looking at organic molecules, are going to be that of covalent bonds. And they're going to arrange themselves accordingly in terms of the different functional groups which are involved in those chemical bonds to make new types of molecules. When we look at the polymers and the monomers, think poly, many. Okay, mono, one. So in other words, what we're looking at are many units that can make one unit, that are made up of one unit, or these one single units can be joined to make many units. So for example, a polymer in a very generic form might be made up of a whole bunch of different monomers hooked together. And in light of this, we're going to have a slightly different property. This could be starch, it could be an amino acid, depending on what type of monomer and polymer we're looking at. At the same time, it's very possible to break these bonds to form monomers. So monomers are smaller units that can recombine to form polymers. Polymers are larger units that can be broken down to form monomers. The three that we're looking at most predominantly are carbohydrates, proteins, and nucleic acids. And we look here in terms of like a monomer. Let's just say, for example, a monomer of glucose, often represented as a single ring chain, or if we look at its chemical properties, it has 6 carbons, 12 hydrogens, and 6 oxygens throughout this particular molecule. If we looked at a bunch of glucose molecules formed and joined together, I'm going to use circles instead of hexagons, a lot easier, we can then get a whole different chemical depending on the organism. This could be something that combines to form cellulose, which is going to be the reinforcement of the cell wall of plants. Or it could have been, for example, a different animal, and this could be something called glycogen, which is a storage unit of glucose. So in other words, these polymers often depend on the organism that is going to take these monomers and form the polymers. These polymers can be structural, such as cellulose. They can be later on functional in terms of storage in light of glycogen. The processes by which these polymers and monomers are going to be made, there's 2 of them: dehydration synthesis and hydrolysis. Think of it this way: dehydration, take water out; synthesis, to make. So we have repeating units of monomers to make a large polymer. Or we think about hydrolysis. Hydrolysis, water, cutting. So we use water in order to break the bonds between the monomers to ultimately from there we get polymers broken down into monomers, or small units. The idea is that either of these, regardless, will need enzymes. So there are going to be enzymes that are going to be involved with the addition or deletion of water in order to make these chemical reactions occur. Water is necessary simply because of the fact that we take water out, we free up some electrons so that the monomers can then join together. And they join together by what is eventually going to be called a functional group. And I'll show you one example, for example, of that of an amino acid, which is often, I think, the easiest to demonstrate. Here's another example of a dehydration synthesis. The water from a reaction in which one hydrogen combines with hydrogen and oxygen from another, frees up the bonds here so that this oxygen can now join to make sucrose, a common table sugar. Remember, water out, dehydration synthesis. When I mention functional groups, what that means is that many of the organic molecules have functional groups. In other words, those which give it characteristics, those which are involved with the chemical reaction. An amino acid, you got what we call an amine group, which is the nitrogen and hydrogens, and we have the acidic group, which is also called that carboxyl. that gives the name amino acid. And it's these functional groups that are going to be involved in forming a chemical bond. So when the dehydration synthesis occurs, I have the amino acid on one side here that is going to then combine with the amine of the other side. So I got a carboxyl group from one and the amine group from the other to combine to form a dipeptide. You're going to notice one thing, that in both of these groups there's something called the R group. The R group is that which is going to be different and what will give each amino acid its particular property. So because this is a dehydration synthesis, we've taken water out, we've now formed a chemical bond. This type of bond is called a peptide bond. And we're going to get into a lot more detail of the peptide bond when we get into our unit of how DNA transcribes and then ultimately translates its message into different proteins. Here's just another example of formation of a larger unit. Remember, it can repeat over and over and over again. So we have monomers, 1, 2, 3, 4, and notice it's these side chains here, or the R group, that is going to make each different amino acid somewhat individual of its characteristic. However, ultimately we're going to get a protein once we recombine these different polypeptides. Lastly, to make sure that we recognize that dehydration synthesis can occur in making the polymers, whereas hydrolysis can occur in order to make the monomers. They are reversible, but it always depends on the enzyme that's going to be involved. Okay?